Hello everyone, welcome to today's video and the first part of my Intro to Calculus series. And I wanted to share with you what I believe is the most important concept in calculus called limits. Now, limits underlie pretty much all the complicated concepts in calculus. Pretty much everything is governed by this idea of taking a limit, and it's basically the cornerstone of all of it. And despite that, it's actually quite a simple concept when you think about it intuitively. And that's what I want to do today. I don't want to teach this as you might see maybe in a classroom or so. I want to teach this with intuitiveness. But in the end, I will show you a more say classroom or so kind of approach, which is a lot more about actually trying to solve for limits in a more mathematical way. And so let's start the video. Now, limits is not that complicated of a concept in reality, which might surprise you as it underlies all of calculus after all. Say we have the limit, alright? Now, let me first show you what a limit really is. Well, the limit, it's basically the entire idea of approaching something and seeing what it's really approaching. Now, this might not make sense, which is why I'll give you an example. Say we have some function, all right, and we have, let me turn the corner actually a bit more down here, and in this function, it goes like this. It has a hole at x equals 1 and goes like this. And its height right now is a 2. So here's my question. What is this function's value at x equals 1? Well, you can see quite clearly there is no value. As I just said, it's undefined for the value x equals 1. But here's my big question. What is its value for x equals say like this value over here, 1.001? Well, we only made it undefined for x equals 1, so clearly over here the value will be 2. As I said, its height's always 2. What about its value for, say, 0.999? Well, that's also y equals 2. Its height will be 2, so when you plug in x equals 0.9999, its y value would be 2. So it's only undefined at 1. Well, you already know this, so what's really a limit here? Well, a limit is saying what, as we keep checking numbers closer and closer to 1, what number does it seem to be approaching? And you might say, of course, it's 2, because no matter how, if we go closer and closer to 1, like we'll still get 2. It's only undefined at 1. But limits doesn't care about the fact that it's undefined at 1. We're not looking at what it actually is. We're simply looking at what it is approaching. Let me give you a slightly different example. Say we have a function that just, I should not have erased the code in the grid. Say we have a function that looks like this. So hole here, it continues on like that, and it's defined here, just over like down. So the value over here is 1, this over here is 2. So now, what is the limit as x approaches -1? Now, if you plug x to be -1 in, you'll find that the answer or y value here will be 1. because that's how we defined it. But limits do not care about the actual value. They care about what it's approaching. So let's see, if I take, like, say, negative 0.999, well, the y value is going to be 2. And vice versa, if I do negative 1.001 or something, I'm still going to get 2. So even though the actual value at x equals negative 1 is negative 1, since limits don't actually care about the real value and they only care about what it's approaching, we can say, alright, this means that the limit, and I'm actually going to show you some real notation here, the limit as x approaches 1, negative 1, is equal to 2. Alright, now I want to try a slightly different example, and I want to attempt to include, I want to attempt to include a slightly different function that doesn't just look like it's just one straight line. I want to show something slightly different. So say we have the limit as x approaches 2 for x squared, this is the function by the way, plus x minus 6 over x minus 2. Well, let's see. If we try and graph this out, and I'll show you in a second, it's going to look somewhat like this. I'll draw with yellow, did it before. Somewhat like this. So it's not just a flat line now. It's still a line, but it's not just a flat line. So what really happened here? What do we really do here? At x equals 2, so we don't really have intuitions. And from this function over here, you might think, oh, clearly this function has no holes. It looks like a continuously defined function. So let's just see what it is at x equals 2, because that's what is going to be approaching, right? So let's see, let's plug x equals 2 in. So we get 2 squared plus 2 minus 6 over 2 minus 2. And let's see, that's 0 over 0. That's going to be a problem. We can't divide by 0. So what is the way to do this? Well, we're going to have to test values really, really close to 2. So say we have 1.9. So we have 1.9 squared, and then we add 1.9, and then we subtract 6, divide by 1.9 minus 2. And now I'll just give you the answer here. That is 4.9. Alright, so when we take a value just slightly to the left, we get 4.9. What if we take a value slightly to the right? Let's see, 2.1. That's slightly more than 2, right? So we should be able to get some good intuition on what it should be from this. So we get 2.1 minus 2, and this is equal to 5.1. Huh, notice something? When we started coming in from the left, we got 4.9. This means that the value somewhere over here is 4.9. The value somewhere over here is 5.1. But this is when we plugged in x coordinates really close to 2, right? So 2 is somewhere between 4.9 and 5.1. Now, if you just throw a lucky guess, you could obviously just say, oh, it's 5. And you'd be correct. But, well, is there a mathematical way to define this? You could obviously keep trying numbers closer and closer to 2. Like, say, try 1.999 and then just try 2.0001 and then just keep closing in on 5. But is there a better, surefire way to just calculate the limit? To just be sure to just calculate this expression. And this is now, if you start to not understand this part, I don't blame you, because this is a more different part if you don't know about limits that much, of course. So if you're new to limits, this might be difficult, but I'll try and show it the best I can. But what you just saw right now is the basic intuition of limits. It is just the idea of approaching a value and trying to see what it is. This is the cornerstone of all of calculus. This is basically what everything is defined from. Now I'm going to show you a slightly different way to do limits. Okay, so a way we try and do it here is we take the function x squared plus x minus 6 over x minus 2, and we try and create a version of this function that is not undefined at x equals 2. So what do I even mean by that? I mean, of course, I could make a ton of these functions. I could just put this and just say, okay, but x is equal to 700. That's not a valid function, but does that mean that it's 700? No. We need a slightly better way to do this. So let's just see. I'll try and show you an example, but let's start with factoring out this top quadratic right over here. If you just see what adds up to be 1 and multiplies up to be -6, you will get to be x equals -2, x minus 2, and x plus 3. And if you multiply this out, they will turn out to be x squared plus x minus 6. And then you divide the whole thing, of course, by x minus 2. Remember, we haven't actually changed anything. All we did is factor the top part, which should not change anything at all, since this is still equivalent to this. Now watch. We can cancel out the x minus 2 and x minus 2 since they're being multiplied over here. And we can say now this is equal to x plus 3. Now you might say, okay, all of these steps were valid because we haven't changed anything of the actual function. We just factor the top side and cancel these out. So what's wrong here? Well, we did actually change the function. Remember why we couldn't define it for 2 before? It's because when we plug 2 into the denominator right there, we would get 2 minus 2, and we'd have to divide by 0. In this final function, there is no division. So if we plug 2 in, we actually happen to get 5. Because just 2 plus 3, and then we just get 5. So what did we change? Well, we remove the denominator. And this is what we like to call a more valid approach of changing the function, because we have changed the function. What we have done is we have kept everything else perfectly the exact same, but we have defined it at x equals 2 just by algebraic manipulation. We haven't actually done anything different. So there it is. This is a more formal way of saying the limit as x approaches 2 for x squared plus 6 minus 6
x squared plus x minus 6, the whole thing divided by x minus 2. This is equal to 5. If that last part didn't make sense to you, it's fine. But all that really matters is this part of it. The intuition. The realization of what limits really are. And I hope you had a really good time today. And thank you for watching my video.